Well, first let me say I'm very pleased to be here. I think this is maybe the second university in Mexico that I visited. And you have a beautiful campus. I hope you appreciate it. Reminds me a little bit of Stanford University, where I'm a professor. This talk is a kind of an unusual talk. It was not created for a very highly technical university audience. But in fact, I think it's an interesting talk because you get some insight as to who Richard Feynman was. And I think by his own admission, he considered himself to be a curious character, which I think is probably an apt description. So let's see, maybe that's too bright. Let's try this one. Yeah, that's probably better. Okay, so I, of course, was an undergraduate when Feynman was teaching his famous two-year course on Feynman lectures in physics. My freshman class started out as 192. CalTech has very small undergraduate classes. And only 120 returned for their sophomore year. Now, I suspect that the Feynman physics was one of the reasons why a third of my class did not return. But of those that did return, almost all of us wanted to become physicists. So I won't tell you that whole story, but Feynman had a profound influence on the 120 that returned. So let's start here. This is obviously just a few things that Feynman is famous for. Richard Feynman's legacy, I think I would say, he was born in 1918 and died in 1988. He developed the theory of quantum electrodynamics that describes the interaction of electrons, positrons, and electromagnetic fields, providing physicists a new way of working with electrons. He produced an alternative formalization of quantum mechanics based on the principle of least action, which allowed him to describe electrodynamics in his own terms, using a matrix of measurable quantities visually represented by a series of graphs known as Feynman diagrams. Produced much later, his Feynman lectures on physics have provided guidance and inspiration to this day, not only to undergraduate physics majors, but to professors of physics as well. And most of the physics professors I know have copies of his volumes. His work on the weak force was crucial to the development of the electroweak theory, and his parton model of the nucleons was important in the discovery of quarks. So much of what I'm going to show you today, this is obviously a PowerPoint, is a visual presentation, comes from a book that was written by Feynman's daughter. It's actually not written, I'm sorry, it was organized. These are, it's a book of Feynman's correspondence. And I was quite surprised at how organized Feynman was. He saved a copy of every letter that he wrote, and every letter that he received was filed. And so it's quite a rare glimpse into the man himself. And I'm not pushing this, but in fact this is, the title of the book is A Perfectly Reasonable Deviation from the Beaten Track, which I guess describes Feynman fairly well. And most of the pictures are coming from the book. So this is the Feynman's family. His father, Melville, was a businessman, and I think the description was that he was not a very successful businessman. Mother was Lucille. Richard Feynman had a sister, Joan, who actually became an astrophysicist. And then, of course, Feynman, I think we all know what happened to Feynman. I mean, he became a very famous physicist. So Feynman did his undergraduate work at MIT and then went to Princeton for graduate study. Actually, it was while he was still an undergraduate at MIT that he became fascinated with this question of the interaction of an electron with its own electromagnetic field. And he carried this fascination with him to Princeton University, where he worked for John Wheeler, who, of course, was a theoretical astrophysicist. He concentrated on the electron in his electric field, as I said, but he also, Princeton University was close enough to New York, where he'd grown up, that he, I would say, became good friends with his high school sweetheart, Arlene Greenbaum, shown here in a picture in 1939. And of course, this is just at the beginning, I suppose, of World War II. So Feynman actually spent only 3 years at Princeton, and the last one was already working on the Manhattan Project. So Feynman then, of course, went to Los Alamos, and so he and Arlene Greenbaum were married, but in fact, over the objections of Feynman's parents, because Arlene Greenbaum had already been diagnosed with tuberculosis. There was no cure for tuberculosis back in those days. Wow. So here's a picture of the two of them as they are, I suppose this is in their wedding attire, I would guess. They were married June 29th, 1942. They then, I suppose that's the car, drove across from New Jersey to New Mexico, where Feynman was working at the Los Alamos National Laboratory, and they found a sanatorium where Arlene Greenbaum would stay then with her tuberculosis. So Feynman wrote many letters to Arlene while they were separated. They would get together for weekends, and a lot of those letters are really quite interesting. This is a picture of Feynman, Richard Feynman, with Arlene in the sanatorium, and I suspect that this was not that long before Arlene died. Feynman would write these letters, and he was a bit concerned that Arlene seemed to be rather demanding of the staff of the sanatorium. So he wrote this, I always am too slow. I always make you miserable by not understanding soon enough. I understand now. I will make you happy now. And then it goes on talking about how he realized at this point that he was really not understanding the condition that she was in. I'm sorry I failed you not to have provided the pillar you need to lean on. Now I am a man upon whom you can rely. Have faith, trust that I will not make you unhappy any longer while you are so sick. Let me use me as you will. I am your husband. I adore a great and patient woman. Forgive me for my slowness to understand. I'm your husband. I love you. And I don't know how, let's see, we have to look at when that letter was written, June 6th. And so here we have a letter. This, by the way, June 6th, that was the last letter he wrote. She died shortly after that. In fact, very, very soon after that. But many months later, I dare say about a year and a half later, Feynman wrote another letter to Arlene, who was, of course, dead. And I know he starts out, Dear Arlene, I adore you, sweetheart. I know how much you like to hear that, and blah, blah, blah. Let's go on to the end of this thing. He says, I know you will assume that I am foolish and that you want me to have full happiness. This is his inability to find any other woman that fascinated him. And you don't want me to be unhappy. I'll bet that you are surprised that I don't even have a girlfriend except you, sweetheart, after 2 years, but you can't, it was less than 2 years, but you can't help it, darling, nor can I. I don't understand it, for I have met many girls, and very nice ones, and I don't want to remain alone, but in 2 or 3 meetings they all seem ashes. You only are left me, you are real, my darling wife, I do adore you. I love my wife, and then he writes, my wife is dead. And the book says that this letter looked very heavily worn, as if he carried it with him and would read it to himself. So following World War II, Feynman came to Cornell for he was a professor at Cornell University, and it was there that he formalized his theory of quantum electrodynamics. However, he never settled down, and that's what the letter was indicating. A feeling of listlessness and dissatisfaction had set in, and he found it hard to teach. He then moved to CalTech in 1951, where he remained until his death in 1988. It was here in 1952 that he married his second wife, Mary Louise Bell, who I think was teaching in some college as an interior decorator, but the marriage did not last and they were divorced in 1956. Feynman then married a third and final time in 1960. His bride, an English woman, was Gwyneth Margaret Howarth. They had a son, Carl Richard, born in April 22nd, 1961, and later adopted a daughter, Michelle Catherine, born on the 13th of August, 1968, and it was, in fact, Michelle Catherine that put this book together. So this is one of the pictures from the book. It shows Richard and Gwyneth together, and I'm fairly certain this was taken in the CalTech faculty club. As an undergraduate, I never got invited to the faculty club. and I always take my freshmen and my graduate students to the faculty club because I try to make up for the fact that I was led a disadvantaged life as an undergraduate at CalTech. Okay, this is Feynman in 1955. I can't tell what he's teaching. It doesn't look like it's a graduate class, but in fact, I think he did mainly teach graduate classes. And then in, I think it was 1960 or 61, CalTech asked him if he would, in fact, teach entry-level physics to the undergraduates. Well, entry-level physics meant 2 years of Feynman physics to all of the undergraduates, whether they were majoring in physics or economics. So it was quite remarkable, but everyone undergraduate at CalTech loved Feynman. The fact that he picked his way into this safe at Los Alamos meant that all of the undergraduates had to know how to pick locks. And we all walked around with lock picks in our wallets. I don't know. And so if you had to, something that was due, where you had to concentrate, you can't do that in the student dorms. So students like me would walk up campus and pick our way into our favorite building. I would usually pick my way into a building that had a coffee machine, so that I would try to get at CalTech it was interesting. People took science courses very seriously, but of course CalTech wanted us to become gentlemen, so every year, every term we had to take a humanities course, and most of us didn't think of these things very seriously. So the idea was to wait until the night before a term paper was due. And then you go up and you stay up all night writing this thing. And since everyone else was doing it, you had no competitive disadvantage that way. Anyway, so Feynman in 1959, it's interesting, he got this idea that in fact one really should start thinking about looking at nature on a very small length scale. And he wrote this article in 59, there's plenty of room at the bottom as opposed to at the top. And he actually offered 2 prizes, each $1,000, and this is 1959. Those were much larger dollars than they are today. Yeah. One was for creating a motor that was less than a 64th of an inch in every dimension. And in fact, when I went to CalTech, that motor was on display in the physics building, and it went around and around and around for virtually every day that I was there as an undergraduate. So it turns out that William McClellan rather quickly built such a motor, which is shown here. This is the motor, but you have to keep in mind that the size of this is very small. It's 0.39 millimeters on the side. So it was quite a remarkable feat, but it wasn't what Feynman wanted. He was hoping that these prizes would force people to come up with new technologies, and that didn't seem to happen. And so after the first, he shelled out $1,000 for the first one of these things, which was quite a bit of money. The second one was supposed to be for a book, for someone's ability to take a page of a book and reduce it in linear dimension by a factor of 25,000. That was, before anyone did that, he basically withdrew the offer of the prize, and he said that after writing his article, he had gotten married and purchased a house and no longer had the money. Anyway, so, but I suspect that that motor is still going around and around at CalTech. This is a letter that Feynman, more than one letter that Feynman wrote to the president of the National Academy of Sciences. I'm a member of the National Academy of Sciences, and I never thought of what I was doing as something which was, in some sense, wrong. But let me just read you a little piece of this. I'm going to put my glasses on, and so I can do this. So he's writing to the president of the National Academy. My desire to resign is merely a personal one. I mean, when they elect you to the National Academy, of course, they don't ask you if you want to be a member. They assume that that's the case. So he says, it is not meant as a protest of any kind or a criticism of the Academy or its activities. Perhaps it is just that I enjoy being peculiar. My peculiarity is this: I find it psychologically very distasteful to judge people's merit. So I cannot participate in the main activity of the Academy, selecting people for membership. And I dare say, I think that's, for most members of the Academy, that is the main thing they do, is they vote for members. So I cannot, to be a member of a group of which an important activity is to choose others deemed worthy of membership into this self-esteemed group bothers me. The care with which we select those worthy of the honor of joining the Academy feels to me like a form of self-praise. How can we say only the best must be allowed in to join those who are already in without loudly proclaiming to our inner selves that we who are in must indeed be very good indeed? Of course, I believe that I am very good indeed, but that is a private matter, and I cannot publicly admit that I do so to such an extent that I have the nerve to decide that this man or that man is not worthy of joining my elite group. So it's kind of interesting. So if you have not made it into the National Academy, you're in a good company. Okay, this is 1962. This is when Feynman was really teaching all of the undergraduates. By the time I was an undergraduate, starting in 1963, he gave what I would call spot lectures to the freshman and the sophomore classes, so that they could at least say that Feynman had taught them when it wasn't really true anymore. And I can't tell whether this is a smoke ring or it's put on the blackboard. I've often wondered what that was, but it was, I mean, he was obviously a very popular teacher, but I think particularly among the 120 that made it to their sophomore year. So I was actually at CalTech when Feynman got the Nobel Prize, and it was announced on October 22nd, 1965. The Royal Swedish Academy has awarded the 1965 Nobel Prize in Physics to Richard Feynman, Tomonaga, and Schwinger for their fundamental work in quantum electrodynamics. And so as an undergraduate, of course, I guess we weren't terribly surprised. This is a picture of Feynman accepting the Nobel Prize from the King of Sweden. And it's sort of interesting, the morning of the 10th of December, the new Nobel laureates will go down to the old opera house and they practice. Okay, so what you do is you reach out to accept the diploma with your left hand, and then underneath that, your hand comes under and shakes, your right hand comes under and shakes hands with the king. And then you bow to the king, and then you bow to the members of the Royal Swedish Academy who are on stage, and then finally you bow to the audience and you go back and sit down. So the year that I got the prize, there was a Polish woman, I believe, that had gotten the prize in literature, and so she did, in the practice, what she did is she bowed to the king, and then she went, and sat down. No one said a word. You don't want to tell a new Nobel laureate that they did something wrong. And so she did exactly the same thing that afternoon. Okay, so I apologize. I do not have access to Richard Feynman's diploma, Nobel diploma, but this is mine. And so on the left side, they're all about the same, I suppose. This is a piece of original art, and actually I quite like mine, much better than most of the colleagues that got the Nobel Prize the same year I did. And then over here, in very nice calligraphy, the Nobel doesn't show up so much here, but it basically says what I got the prize for in Swedish, and then here's my name in multi-colors, and then at the bottom is the seal, etc., etc. So, of course, you also get a Nobel medal, and this is all the front of every Nobel medal looks the same. It all looks exactly like this. Now, I looked into this recently. They're not pure gold. It's something called green gold, which is 20% silver, 80% gold. I was wondering when the price of gold got up to $1,300, how much, whether I could get a good camera lens by selling this thing. Anyway, so the back, though, is different. And so for the natural sciences, you can't read this for all. This says natural sciences. You get these two women here, and they're not wearing a lot. And then it has my name, and of course the year is Roman numerals, so it looks very modern that way. No, it doesn't look modern at all. So anyway, Feynman got this. Now back when Feynman got his prize in '65, there was a ball after the grand dinner, which is held that evening. So someone actually, and I didn't know that Feynman could waltz, but I suppose he could, or at least you can't tell that he can't by looking at the picture. So this is Gwyneth and Richard, and when my prize was announced, someone sent me a CD of waltz music and said, Osheroff, you'd better get busy. But in fact, I didn't have to waltz, as it turned out. So then, of course, you get lots and lots of telegrams and people from all over the world wishing you, congratulating you, and best wishes and all that. So the first one of these actually writes, Dear Richard Feynman, California Institute of Technology, Pasadena, California, congratulations on your well-earned achievement. Our best wishes, Jules and Rosalie Greenbaum. And Feynman answered every one of these things. Dear Rosalie and Jules, I was surprised and happy to learn that I'd won the prize, but to hear from you stirs memories of long ago. You, too, must remember someone who would have been really happy on this day. And of course, wow. This is Arlene's brother and written the original congratulatory note. And then, of course, there has to be one from the President of the United States, at least in this year, not when I got the prize. Yes, so who was president in 1966? Anyway, I didn't vote for them again. Okay, good news. So this is Lyndon Johnson, who is just recovering from gallbladder surgery. And so he says, good news is always good medicine. I was delighted to learn of your winning the Nobel Prize in Physics. The nation is grateful for your example, and I am personally thrilled to share in your happiness. Well done. And then he replies, one of the great pleasures of being awarded the Nobel Prize in Physics was to receive your telegram. I was surprised, honored, and delighted by it. May the news continue to be good and quickly restore your good health. Richard Feynman. And so then, of course, the undergraduate students have to outdo everyone else. And I had nothing to do with this, but you can barely see it up here. There's a big poster that says, I can read it on here, Win Big RF, Richard Feynman. And so Richard Feynman wrote to Tom Daly, who was the instigator of this thing. I don't know how he found that out. It says, Dear Tom, you certainly found an appropriate card to congratulate me. That great sign on True Paul, which doesn't exist anymore, was to me one of the most exciting and meaningful signs of congratulations that I have received. Please accept my thanks and convey to all of your cronies who risked their lives to put it up how much I appreciated it and enjoyed it. So I'm sure that the CalTech administration did not share in that. Anyway, so I think the key to Feynman's development was really Feynman diagrams. So here we have an electron and a positron coming in, annihilate, you get a gamma ray, and then gamma ray decays into a quark and an anti-quark and a gluon. And so this is actually really a shorthand way of writing down these sort of processes. But in fact, typically in any complicated process, you don't just have one Feynman diagram. It would frequently be an infinite number of Feynman diagrams. And so you just have to, I mean, you don't usually write them all down, but you start by writing a few of them. So here's an example. This is actually Kenneth Wilson, who was a high energy theorist, ported renormalization group theory to condensed matter physics. And so he's trying to explain oh, come on, what is it? I'm so bad with names now. Where you get, conduction electrons get polarized by an itinerant electron. What's that called? Come on, please. What?
Oh, God.
The Kondo effect. Yeah, right. Good. I should have written that down. Anyway, and so here are some of the Feynman diagrams that are associated with that process. And this is, of course, I think, asymptotic freedom in quantum chromodynamics uses Feynman diagrams as well, more complicated looking ones. Oops. What? How come this thing's not? What's going on? Here we go. Okay. So, electron-phonon interaction, superconductivity, polarons. Bardeen Cooper-Schrieffer, of course, got the Nobel Prize for explaining the origins of superconductivity in 1957, and then later on, Tony Leggett actually explained I would say a lot of the properties of superfluidity in helium-3, which I had observed. So here is an electron, and it creates a phonon, which in fact it goes through the lattice, and basically that mediates the interaction between two electrons, and of course that is the correlation which leads to the development of a Cooper pair. And it's Cooper pairs that condense. You can't have electrons condensing because they're Fermi particles. And so here's, skip that. Things get more complicated with superfluid helium-3 because there's no lattice. So how do helium-3 atoms, which are spin 1/2 particles, create these correlated pairs? And it's basically through the formation of a cloud of parallel spin polarization on the outside, and these are the Feynman diagrams that one must sum in order to figure out what's going on here, the internal states. Feynman also actually was involved in understanding superfluid helium-4. Now, helium-4, of course, superfluidity was actually first created in I think, probably 1908 when Camerlionis first liquefied helium. What he tried to do then was to find out where helium solidified. This is what Dewar had done with hydrogen. So he pumps on the vapor above the liquid and he cools it off. And he did this experiment for 2 solid years, ultimately reaching a temperature of 1.04 Kelvin. And of course, helium remained in a fluid state. And the reasons for that have to do with quantum mechanics, which was just being developed at that time. But I personally have cooled helium-3 down to 1/10,000th of a Kelvin. It still remains very happily in a fluid state. So there's no answer to that problem. But what Feynman did, looking at helium-4, if you look at the excitation spectrum, you see a linear part. These are the phonons. And then there's this turnaround, and you have this rather broad minimum. And no one really knew what that was all about. And Feynman suggested, in fact, that that's basically a quantum of what do you call this? Smoke ring, essentially. That as one atom goes through, the other atoms have to go around the outside of that. And to this day, that is the way physicists think about the Roton minimum. Feynman, of course, was also a father, and so I like this picture. It looks like he's lost. So Michelle and Carl are on a camping trip with Feynman, and he has a map, and he certainly doesn't look very happy in that picture. So maybe I'm reading too much into his face, but it really looks to me like this. So this is sort of interesting. I'd actually met, I'll talk more about that later, Michelle Feynman when she was 16 years old. And she told me about this Feynman diagram. Feynman put the Feynman diagrams to decorate his van. So this is Lucille, Feynman's mother, Gwyneth, his wife. This is Richard. This is Michelle, and this is Carl. And is going somewhere on a trip. It's sort of interesting. Feynman actually won rather few prizes before he got the Nobel Prize. And I think that's certainly today that doesn't happen very often. Frequently you get other prizes first. So Feynman got some of those other prizes afterward. Here he's receiving the Niels Bohr Medal from the Queen of Denmark in 1973. And here he's receiving the, I guess I call this National Medal of Science from Jimmy Carter in 1979. He writes, "It was good to get to know you and other members of the staff at the plant." I have a plant, I suppose that means the White House or something like that. So this is a picture, I mean, we could go on for a long time, but I'm not going to, of Feynman and Gwyneth on their silver wedding anniversary. I don't know if people in other countries know that means the 25th wedding anniversary. Yeah. And if you look in the background, you see Feynman diagrams, a very interesting painting, which I've seen before, actually. So Feynman, at this point, already was sick with stomach cancer, and it wasn't clear how long he could survive. But Feynman took on one last task. He was asked to be on the Rogers Commission that investigated the Challenger space shuttle accident in 1986. And here's Feynman making some sort of a point, obviously. And I would say what Feynman did on this was something that probably no one else could do. But it wasn't that it took a very bright person to realize that when you cooled rubber down, it became hard. However, for Feynman to show that in front of all these newscasters and people like that, I think the point was made very strongly. That in fact, this is not rocket science. It is very simple stuff. It's actually much worse than that if you really go in, read anything part of the Rogers Commission report. They recovered the solid rocket boosters. That's where these O-rings were that leaked. And they would notice that the O-rings had been ablated maybe a third of the way through by hot gases. And in fact, in almost every launch, you'd see puffs of black smoke coming out from the SRBs, as they're called, solid rocket boosters, on launch. And so, of course, this idea that the O-rings should be ablated a third of the way through, that should have never happened. And later, I was on the Columbia Accident Investigation Board, and we created a term that described this habit of NASA, which we called normalization of deviance. So some part of this very complicated system misbehaves, and you say, well, that, and you can't stop it from doing that. You say, this is the normal way of it sealing, in this case, the O-ring. Of course, it never was. And so after it was all over, Feynman wrote something. And it's sort of interesting. The Rogers Commission itself didn't say very much about management's role in this disaster, which was, in fact, extreme. But because it went back a long time, I mean, they knew that these O-rings leaked gases through. But they never did anything about it. And so this is a letter that Feynman wrote to the head. So this is, I don't know if I can get this thing to work now. This is the launch video showing Columbia here. And let me see if I can get this thing to work. I have to come down here and, no, come on. Oh. It doesn't,
Oh, computers, yes. Were they?
Well, it's just not going to give me, there we go.
Okay.
So do people see that? Let me see if I can go back. Okay, so what you'll see is a piece of stuff. It looks like it's going up, but that's just the perspective is bad. And a piece of stuff's tumbling, it breaks into two, goes underneath the left wing, then you'll see a spray of debris coming down. So let me try that again.
Yeah.
There we go, there it is.
Oh, yeah.
And now, that's it. The engineers that saw that were gravely concerned and had informally asked the Department of Defense to use their spy satellites to image the left wing of Columbia to see whether there was a hole or not. Linda Ham, who is the head of the mission management team, when she learned of this, because they had obviously gone around her authority, was really mad, and apparently, and turned off the request.
Really?
Yeah, and she should have been the one to have requested it in the first place. Anyway, I think Linda Ham is now working for NASA at the South Pole. She was not fired, actually. It was interesting.
No? Really?
Yeah, that's okay. So Richard Feynman died of stomach cancer on February 15, 1988, less than 2 years after he served on the Rogers Commission. His wife also died of cancer roughly a year and a half later. And it's sort of interesting because what you can get on the internet now is absolutely amazing. I was once at UC Davis and I had to give a public lecture. And I said, well, okay, I'm going to be there for a whole week, so I won't start putting this lecture together until I get to UC Davis. But then, nowadays lectures all have lots of visuals in them. We're used to that. It's like eating candy or something like that. But I just downloaded everything off the internet. It's really wonderful. So in fact, this came from off the internet. So this, in fact, is a picture of the grave marker of Feynman and his wife. The dates are shown here. And then this is a broader view. It's this grave marker here. Now, if you happen to be in Altadena, California, and you want to stop by to pay your respects to Feynman, at least in memory, they're so helpful. They even give you the latitude and longitude, so you can take your GPS, and that way you won't get lost. I mean, I don't know about you guys. When I go into a cemetery, I get lost very quickly. So I would say that Feynman's epitaph was written by Julian Swinger, one of the people he shared the prize with. Feynman was an honest man, the outstanding intuitionalist of our age, and a prime example of what may lie in store for anyone who dares to follow the beat of a different drummer. And I suppose that is where that all came from. And finally, now this is fun. Okay, this is Feynman at his best, I think. Here is my favorite story about Feynman, which came to me from Michael Peskin up at SLAC. He quotes extensively from Yadish Mara's biography, To the Beat of a Different Drum, Oxford Press, 1994. And it goes, at the 1949 APS meeting, Murray Slotnick presented new results which he had obtained after 2 years of calculation concerning the interaction between an electron and a neutron. He had found the answers for the pseudo-scalar theory and the pseudo-vector theory were different. In fact, in the case of the pseudo-vector theory, the answer was logarithmically divergent, but for the pseudo-scalar theory, the results were convergent and gave well-defined answers. Oppenheimer was in the audience, asked Slotnick, well, what about Case's theorem? By this he meant the new result by Kenneth Case, who at that time was a postdoctoral fellow at the Institute for Advanced Studies at Princeton, which were going to be reported the next day. Oppenheimer was then the director of the Institute. Case had announced that he had proved that the results for both the pseudo-scalar and pseudo-vector theories were the same. Slotnick answered, I've never heard of Case's theorem. Feynman had missed Slotnick's talk, but somebody asked him about the discussion between Oppenheimer and Slotnick. Feynman went to Slotnick and said, look, I'm very anxious to try out if I understand what these things mean, that is, his Feynman diagrams, I suppose. So just tell me what you did. Slotnick replied, I scattered the electron off the neutron and I had correction due to the mesons. Feynman described what happened next as follows. This was a welcome opportunity to test my guesses as to whether I really understood what these two couplings were. So I went home, and during that evening, I worked out the electron-neutron scattering for the pseudoscalar and pseudovector couplings, saw that they were not equal, subtracted them, and worked out the difference in detail. The next day at the meeting, I saw Slotnick, and I said, Slotnick, I worked it out last night. I wanted to see if I got the same answers you do. I got a different answer for each coupling, but I would like to check in detail with you because I want to be sure of my methods. And Slotnick said, what do you mean you worked it out last night? It took me 6 months. And then when we compared our answers, he looked at mine and he said, what is that Q there, that variable Q? I said, that's the momentum transferred by the electron. The electron deflects off different angles. Oh, he said, no, I only have the limiting value as Q approaches 0 for forward scattering. Well, it was easy enough to just substitute Q equals 0 into my answers as he did, but it took him 6 months to do the case for 0 momentum transfer, whereas during one evening I had done the finite and arbitrary momentum transfer. This was a thrilling moment for me, like receiving a Nobel Prize, because it convinced me at last I did have some kind of method and technique and understood how to do something that other people didn't know how to do. That was my moment of triumph when I realized I had succeeded in working out something worthwhile. As Feynman further recalled, the next day, Case reported his theorem at the APS meeting. And just to be annoying, when Case finished, I said, yeah, but what about Slotnick's calculation? And then he goes on and says, you know, I mean, Oppenheimer was so imperious. If Case proved the theorem, it must be true. And I argued, what about Slotnick's calculation? That theorem can't be true. And everybody laughed because it was perfectly logical to suppose that the theorem was at fault, not the calculation, you know. So Oppenheimer said, well, maybe Slotnick's calculation is wrong. And I said, no, I checked it last night and it's all right. So if you are, I think in Feynman's case, he was a great physicist, but his personality made him absolutely bigger than life. And eventually, of course, Feynman got his picture on a postage stamp. When that happens, of course, that is the pinnacle of success. Now, if you can't see it right here, but this postage stamp, it has a date on it, which is 2005. So Feynman had been dead for many years. Unfortunately, he didn't probably know that he got his picture on a postage stamp. But the question is, given the fact that he was dead, what image did they take? And it's kind of interesting because it is, in fact, the image that I showed in my first slide, Feynman with his bongo drums. It's exactly the same image. So Feynman, of course, that's another thing. In fact, all of these books that surely you're joking, Mr. Feynman, at starting, that was the first one, this particular one resulted from Feynman would play the bongo drums with Ralph Layton. This is Bob Layton's son, Bob Layton of Feynman, Layton, and Sands. Yeah. And so they would record these things, and eventually, and Feynman would tell these funny stories about his life. And so I think it was Ralph Layton that put all these things together into a book. And to my knowledge, Feynman actually never wrote a book. Typically what would happen is Feynman, for instance, the messenger lectures at Cornell, he would give a series of lectures and people would write a book based on those lectures. Well, that's a good question. I don't know whether he reviewed them or not, but in fact, he wasn't a prolific writer. There's no question about that. But he loved to lecture. So now there's one other thing I want to talk about, and that is, in fact, I think this is actually done now at UC Santa Barbara in 1975. Yes, UC Santa Barbara. In 1975, Feynman gave a talk on what he was doing at Los Alamos during the war years. And so we can hear this, I hope. I'll take my computer. Let's see if I can get the sound up a little bit. That's okay. Here we go.
Well, it's almost finished.
Can you guys hear this?
The next thing that happened was, of course, the test. After we made the calculation, we had to make the test. I was actually at home on a short vacation at that time because my wife died. And so I got a message that said the baby was expected on such and such a day. So I flew back, and I just arrived on the site while the buses were leaving. I couldn't even get to my room. And I got out to the site, and we waited out there at the distance. We were 20 miles away. And we had a radio, and they were supposed to tell us when the thing was going to go off and so forth. The radio wouldn't work, and we never knew what was happening. But just a few minutes before it was supposed to go off, the radio started to work, and they told us there was 20 seconds or something to go. The people that were far away, like we were, the others were closer, 6 miles away. And they gave out dark glasses that you could watch us. Dark glasses. We're 20 miles away from the damn thing. We think it's dark glasses. They're going to see a damn thing through dark glasses. And so
you hear the Brooklyn accent.
The only thing that really hurt your eye, bright light never can hurt your eye. It's ultraviolet light. So I got behind a truck windshield. So the ultraviolet can't go through glass, so that would be safe. And so I could see the damn thing. Other people never could see the damn thing. Okay, time comes. And this tremendous flash out there. So bright, my head goes like this because it was so bright. And I see this purple splotch on the floor of the truck. And I says, that ain't it. That's an after. So I turn back up and I see this white light changing into yellow and then to orange. The clouds form and then they disappear again. The compression and the expansion forms and makes clouds disappear. And I saw, and then finally a big ball.
A big
Is that?
Well, it's almost finished. The next thing that happened was, of course,
Hold it, I have this somewhere else. This is too fun for you guys to miss. So let me hide PowerPoint. PowerPoint. So let's go. I think it's in here. Okay. Okay. What's going on here? Play.
Well, it's almost finished. The next thing that happened was, of course, the test. After we'd made the calculations, we had to make the test. I was actually at home.
Oops.
At that time, because my wife died. And so I got a message that said the baby was expected on such and such a day. So I flew back, and I just arrived on the site while the buses were leaving. I couldn't even get to my room. And I got out to the site, and we waited out there at the distance. We were 20 miles away. And we had a radio, and they were supposed to tell us when the thing was going to go off and so forth. And the radio wouldn't work, and we never knew what was happening. But just a few minutes before it was supposed to go off, the radio started to work, and they told us there was 20 seconds or something to go. The people that were far away, like we were. The others were closer, 6 miles away. And they gave out dark glasses that you could watch us. Dark glasses. We're 20 miles away from the damn thing. We think it's dark glasses. They're going to see a damn thing through dark glasses. And so when I figured, the only thing that really hurt your eye, bright light never can hurt your eye. It's ultraviolet light that does. So I got behind a truck windshield, so the ultraviolet can't go through glass, so that would be safe. And so I could see the damn thing. Other people would never could see the damn thing. Okay, time comes. And this tremendous flash out there, so bright, my head goes like this because it was so bright. And I see this purple splotch on the floor of the truck. And I says, that ain't it. That's an after image. So I turn back up and I see this white light changing into yellow and into orange. The clouds form and then they disappear again. The compression and the expansion forms and makes clouds disappear. And then finally a big ball of orange. It became a center that was so bright, became a ball of orange. It started to rise and billow a little bit and get a little bit black around the edges. And then you see it's a big ball of smoke with flashes on the inside of the fire going out of the heat. And I saw all that, and all this that I just described in just a moment took about 1 minute. It was a series from bright to dark, and I had seen it. I'm about the only guy in the world that actually looked at the damn thing, the first Trinity test. Everybody else had dark glasses. The people at 6 miles couldn't see it because they were all told to lie on the floor with their eyes like this. So nobody saw it. And the guys up there where I was all had dark glasses. I'm the only guy I saw with the human eye. Finally, after about a minute and a half, suddenly there's a tremendous noise. Bang! And then rumbles like thunder. And that's what convinced me. Nobody had said a word during this whole minute. We're all just watching quietly. But this sound released everybody. It released me particularly because the solidity of the sound at that distance meant that it really worked. The man who was standing next to me said, when the sound went off, "What's that?" I said, "That was the bomb." The man was William Lawrence, who had come. He was going to write an article, he was going to describe the whole situation. I had been the one who was supposed to have taken him around. It was found that it was too technical for him, and so later Mr. Smythe came around, and I showed Mr. Smythe around. When I was showing Mr. Smythe around, we went into a room, and there on the end of a pedestal, a little narrower than that, was a small ball about so big, silver-plated. You could put your hand on it, it was warm. It was radioactive, it was plutonium. And we stood at the door of this room, talking about it. There was a new element that was made by man that had never existed on the earth before, except for a very short period, possibly at the very beginning. And here was all isolated, radioactive, and had these properties that we had made it. And so it was tremendously valuable, and nothing more valuable, and so forth and so on. Meanwhile, he's sort of, you know how people do when you talk, you kind of diggle around and jiggle and so forth. He's kicking the door stop, you see. And I said, yes. And I said, and the door stop is appropriate to the door. So the doorstop was a hemisphere, yellowish metal, gold, as a matter of fact. It was a gold hemisphere about so big. What had happened was we needed to do experiments to see how many neutrons were reflected by different materials in order to save the neutrons so we didn't use so much material. And so we had tested many different materials. We had tested platinum, we had tested zinc, we had tested brass, we tested gold. And so in making the tests with the gold, we had these pieces of gold. And somebody had the clever idea to use that great ball of gold for a doorstop for the door that contained the plutonium, which is quite appropriate. After the thing went off, there was tremendous excitement at Los Alamos. Everybody had parties. We all ran around. I sat on the end of a Jeep and beat drums and so on, except for one man that I remember. His name was Bob Wilson, who got me into it in the first place. He's sitting there moping. I said, "What are you moping about?" He says, "It's a terrible thing we made." I said, "But you started. You got us into it." You see, what happened to me, what happened to the rest of us, is we started for a good reason. Then we're working very hard to do something, and to accomplish it is a pleasure. It's excitement. And you don't stop to think any, you just stop. After you thought at the beginning, you stop thinking. So he was the only one who was still thinking about it at that particular moment. I returned to civilization shortly after that. I went to Cornell to teach. And my first impression was a very strange one, and I can't understand anymore, but I felt very strongly then. I sat in a restaurant in New York, for example, and I looked out at the buildings, and how far away I would think, how much the radius of the Hiroshima bomb damage was and so on. How far down there was, down to 34th Street, all those buildings all smashed up and so on. And I got a very strange thing. I would go along and I'd see people building a bridge, or they're making a new road. And I thought, they're crazy. They just don't understand it. They don't understand. Why are they making new things? It's useless. But fortunately, it's been useless for 30 years now, wasn't it? Almost. Maybe we'll make 30 years. So I've been wrong for 30 years about it being useless to make bridges, and I'm glad that those other people were able to go ahead. But my first reaction after I was finished with this thing was, it's useless to make anything. Thank you very much.
Well, let me see. I think
I'm sad to say that that would have been a great place to stop, but I think I have a few more slides here. But it's really, I found it just absolutely amazing to hear Feynman talking about how he felt after helping to create the bomb. Now, if you get the whole thing, I think it's maybe an hour or more, and it's I have it on my computer. If anyone wants it, give me a USB stick. It's just listening to the whole thing is really quite amazing. Feynman, you know, he wasn't a Pauli or one of these very powerful people when he was, I mean, he didn't even have his PhD when he went to Los Alamos yet. So he was a small person. He was in control of a room full of women using mechanical calculators to calculate numbers. And it's interesting, they of course completely overworked these calculators, so they kept breaking down. They were supposed to send them out to Marchand to get them fixed, but in fact they didn't come back very fast, so they figured out how to fix them themselves. Anyway, it's a really interesting thing, and Feynman is well, dark glasses. He could not have said it any better than that. Dark glass. Anyway, so let me see where's PowerPoint here. Okay, so we're done. So now, the thing I haven't told you about is that I guess it was, I can't remember what year anyway. CalTech was trying to hire me, and so I was. I mean, this was my alma mater's, so you had to take this seriously, and I was down there, and I felt that I wanted to pay my respects to Feynman. Everyone knew he was. It must have been around the time that he died. And so I would go to his secretary. And his secretary was actually, she felt her job was to kind of scare people like me away, not bother the boss. And so it was the third time I'd come up to her, I was arguing with her, and Feynman comes up. And I said, oh, Professor Feynman, I'm so happy I got a chance to meet you. He says, come on in my office. And I said, oh, I'm Doug Osheroff. I said, I know who you are. We're trying to make you a faculty offer, for God's sake. And so we sat down and started talking about crazy things like the fact that hydrogen can diffuse through, I guess it's palladium or platinum, I can't remember which anyway. But we had a lot, and so I said, Feynman had very few graduate students, and the only one I know was Phil Plassman at Bell Laboratories. And Phil had claimed that Feynman had agreed to visit Bell Laboratories in July. And so I said, I reminded him of that. And he said, what does Phil Plassman know? As if he hadn't agreed to that. And so I said, you shouldn't come in July. It's a terrible time. It's so hot and humid. Why don't you come in May? It's very nice. He says, I can't come in May because I have to go up to Boyce McDaniels. This is the director of the Cornell Synchrotron's 60th birthday symposium. So I said, if you're going to Cornell, you have to pass through Newark Airport. Give us 24 hours. And he thinks about it. He says, okay. And then he says, no, I'm going to have my daughter, Michelle, with me. And I says, what is Michelle interested in? And he says, well, only one thing, horses, jumping horses. So I said, I knew someone at Bell Labs whose wife ran a stable for handicapped youngsters. And so I said I could take Michelle out and she could spend the day with Octavia Brown. And so that sounded very good. And the time came, Feynman shows up and everything, and that I drive Michelle out. And it turns out that there was some miscommunication, and Octavia Brown never showed up. Great. So I said, well, Michelle, what would you like to do? And so she says, well, why don't we visit Princeton? Of course, that's where her father got his PhD, sort of. And so we visited Princeton, and then we came back, and I guess we came back still about 45 minutes before Feynman's lecture, and the Arnold Auditorium at Bell Laboratories was totally packed. I mean, there was no standing room left. Luckily, they saved 2 seats for us in the front row. And so Feynman started to talk, and I didn't know what he was going to talk about. And he starts talking about reversible computers. Any process that happens reversibly has to happen very slowly, or it won't be reversible, right? So I was very disappointed in this topic. So he talks for about 45 minutes, and this is the year before he died, and so that was probably quite a bit of effort on his part. And so the talk's over, and he calls for questions. So the talk went for about 45 minutes. The questions went for an additional 45 minutes. But the first question was really interesting. Some guy stands up and says, is there any more physics in this business about reversible computers, or have you done all the physics and it's going to be engineering from here on out? And Feynman stands up on his tiptoes, looks over the lectern at this guy who was in about row 5 or something. He says, "What do you mean, physics? It's engineering. It's all engineering." Anyway, but the questions just kept coming after that. It was quite interesting. And that night, I remember we went out for dinner at a Chinese restaurant. Anyway, that was kind of fun. It was my only recollection of meeting Feynman on roughly equal terms. Before, I had only been a tiny little student, of course. Anyway, that's all I can say about Feynman. This has not been a deep lecture, but I hope you've enjoyed it. Thank you very much. I suppose if people want to leave, I will understand. Does anyone have any questions? No, it's not the kind of talk that. Yes, ingenuous questions. Yes.
Yes. What would you think that Feynman would say to the youngsters that want to be physicists?
Oh, gee, I would guess that Feynman was so much in love with physics that he would encourage students to go in that direction. Now, if you look back at Feynman's past, what you find is that his father, who was a businessman, would walk around with Feynman in lower Manhattan, explain why the sky was blue and sunset was red, and all of these sorts of things that we all teach our students in entry-level college physics. He would also give Feynman sort of math problems to work. And so I mean, I think this kind of thing, if you want to make your child into a physicist, do what Feynman's father did. And I think, because what happens is, particularly Feynman was phenomenally capable at mathematics. And I think that having worked on these problems when he was young really wired his brain very well for doing those sorts of things. I find that I think he loved physics so much. And he, of course, had a very broad view of physics. It wasn't just quantum electrodynamics. Any other questions? Well, thank you all for coming.